Hi, this is E637. I'm Charles Bouman, and we're going to be picking up the material on color imaging and XYZ. So let me switch over to the computer. Okay, so we talked, let me just review briefly. When we last left our superhero, he was covering XYZ chromaticity coordinates. Oh no, well, I'm sorry. He was actually not covering that, whoever he is. Yeah, okay, anyway, we had tristimulus colors, R, G, and B, okay? And each of these is, by the way, the uppercase boldface R, G, and B represent the primary colors. So that's like a vector because it represents the spectrum of colors, okay? That's why it's boldface and uppercase, because it's a vector. I should also mention, I don't think I mentioned this last time, that on a computer, obviously, you can't really deal very effectively with the continuous function of anything, right? But so what you have to do is discretize it. And by discretize it, what you really mean is you're storing some parameters which describe a continuous function is one way to think of it. So you can use either some continuous spline interpolation of discrete points, or you could just sample it. You can think of it as just being sampled. That's typically how people think about it. There's more sophisticated ways, but that's typically how people think about it. And a typical situation is you sample with 10 nanometer samples. So, okay, so you go for 300 nanometers to 400 nanometers to 700 nanometers. Sometimes they go further, but that's a typical case. And can we switch to the pad so I can just draw this? So you go from 400 nanometers to 700 nanometers. So this is longer wavelengths. Longer wavelengths mean lower frequency. Mean lower frequency. So here you're doing it sort of the frequency is increasing in this direction. Over here is ultraviolet, and over here is infrared. This is the near infrared, and then if you get far into infrared, that's the far infrared, right? So typically what they do is they break this up into 10 nanometer steps. Okay, so, and when I say 400 nanometers, I mean the sample sort of centered at 400. You take one sample at 400 nanometers, so it kind of really straddles it, and one at 700. So if you calculate, if you take 10 nanometer steps, then let me see, 700 minus 400 is 300. Divide by 10 is 30, but because you get the sample at the beginning and the end, it becomes 31 samples. So on a computer, the way you'll usually represent this is a 31 sample vector. So a 31 sample vector gives you the spectrum of the signal. Okay, now, one thing to keep in mind is if you have I of lambda, okay, so the way that will be represented as, let's say, I, okay, which is now a member of R to the 31, okay? But if you have something like X of lambda, we talked about the X0 of lambda, that's the color matching function, right? Now, that's going to be represented as X0, which is also a member of 31, right? But X0, you usually think of this thing as a row vector, okay? And you usually think of this thing as a column vector. And the reason is that this is data, but X0 is sort of not data. It's an operator, right? So the distinction is kind of a subtle one, perhaps not completely rigorous, because you can think of it perhaps both ways. But the dominant view is that this thing's an operator because you take X0, right, and you multiply it, so it's a row vector, you multiply it by I, that gives you the inner product, and the result will be oh my gosh, I'm using the wrong letters. Sorry about that. This is supposed to be an R0. I got ahead of myself. I haven't told you what X0 is, so you don't know yet. Okay, R0. Okay, and then I multiply that, and then I get R. And this thing here is a scalar, right? And now if I take R, okay, if I take R and I multiply it by R, now I'll get a scaled version of the primary, but this color won't be the same as the original I. It'll just have the same component of that primary. So we'll talk about that some more. So the main thing that I just wanted to point out is that the basis vectors in this, or the vectors in this space, are 31-dimensional. And they come in two flavors: data, which is a spectrum, and operators, which are like these color matching functions. That's why it's called a color matching function, okay? Okay. So the confusion comes in where people will often think of the color matching functions as data, as if they're like a spectrum. They're like a color. They're not. Okay, so let's go. That's an interesting point to ponder there for a moment. Okay, so we talked about all the color matching experiments and so forth and so on. And from that you extract out the color matching functions. So these are color matching functions. So you plot them. They're like 31-dimensional Oops. Is it okay? Okay. They're 31-dimensional quantities, right? And you plot them like this, and you look at them and you go, well, that kind of looks like the spectrum of something, right? So you say, well, I could... and this looks like it's a red spectrum. But this is not a spectrum. This is a function, because you take this function, you multiply it by the spectrum, you integrate, and that gives you the output, okay? And frankly, it causes confusion. It'll cause you, I guess it's a free country. You can think about it any way you want, as long as you give me the right answer on the exam. Okay? But I'll warn you, it'll cause you confusion if you think of this as a spectrum, because it just really isn't. And one way in which it very clearly isn't is it's negative. I mean, how would you have a spectrum that's negative? And later we'll see all three of these are at least a little bit negative. Okay? So now, so these are now negative. So these are functions. If you take the inner product of each of the these, so if you take R0, B0, and C0, so could we switch to the pad again? So if these are now row vectors, and I multiply them by I, okay, and then I'll get out RG, what am I talking about? B. What am I talking about? RG. Oh my gosh, I'm completely losing my mind. Okay. The drugs are just starting to take effect, I guess. Okay. Anyway, okay, so here we go. R, G, and B, right? Okay, there we go. So then I got R, G, and B, okay? Right? So let's just visualize this. This looks like this. We got a row vector there, and we have times a column vector, right? And when we take the product, we get a scalar out, right? Okay. And these are both 31-dimensional, okay? Now these three values are the tristimulus values. There might be two M's in tristimulus, except for I didn't have enough space, so I left one of them out. Values. Okay. So if I take R times R, and then plus G times G, okay, plus B times B, okay. Now, what that means is I'm taking R, which is a scalar, times the column vector plus G times a column vector plus B times a column vector, right? So what I get out here is also a column vector, okay? And what I'd like to say is that this equals I, okay? So by equals, I mean that the colors are the same, there's only one problem, which is they're not equal. Okay, so they're equal in the sense that this color will look like that color, but they're not equal in the sense that the vectors of 31 components will not be equal. So I'll put like a question mark here, because they're sort of equal, but they're not equal. What it really means is that confined to the subspace associated with the color matching functions, the projection onto that subspace is equal, but outside that subspace they can be not equal. So these are metamers. Metamers. Okay, and metamerism is what you have. It's the quality that occurs when two things look the same color, even though the spectrum are different. The spectra are different. Okay, so these actual vectors are not equal, but the subspace spanned by when you look at them, they're the same because your eye is only sensitive to a subspace. Okay, and they're equal in that subspace. Okay, now. So is that clear?
Is this eye the same?
Yeah, same as this eye up here, because that's why we took the color matching functions. Now these red, green, and blue primaries can't be just any red, green, and blue primaries. They have to be the ones that produced these color matching functions. Because remember, the color matching functions will depend upon the primaries. Because when we did the experiment, our experiment was premised on picking specific matching colors with specific primaries. If we change the colors of the primaries, then our match will shift. Okay, so and for the CIE color, let's say 2-degree observer color coordinates, they specified exactly what these color primaries needed to be. So in that case, the experiment's well formulated, and you'll get specific values of R, G, and B, which are the tristimulus values, okay? And then you'll know how to reproduce the color. So you give me basically a spectrum of light, and I can produce another spectrum of light which will appear the same color if the surround is the same. If the surround's not the same, of course, the color will appear different, okay? Because, as we saw before, the same color, something which is a perfect spectral match can look like a completely different color, okay, depending upon what its surround is. But all things being equal, these two colors will match. The two patches on a background that's the same will look to be the same color, even though the spectrum are different. The spectra are different. Okay, does that make sense? Okay, now, yeah.
My monitor is one color and your monitor is another color. How can we make these two environments transferable, and how can I say that, okay, this color is equal to that?
In other words, if the surround is different, right, how can I know that the colors will look the same?
Yes.
Well, first of all, if the surround's different, then in order to get a color match, you actually have to have two different. The spectra have to actually be different in order to produce the same color, the same perceived color.
Right.
Okay. And people do that. You have to adjust the colors. We'll talk about that in a very cursory way. Okay. But the answer to your question is we won't do that. Okay. Okay. First of all, we're not going to study that problem. Okay. And second of all, because it's a hard problem. So our assumption is that you'll have total control of the surround of the environment, and you'll match all the colors in the entire environment. They may not be spectral matches, but they'll be tristimulus matches. Okay. So they'll be metamers. And in that case, you'll be effectively presented with the same stimulus, so your response will be the same. What it will be, we don't know, but it will be the same. Okay? So this is like, it's like you have a video coding algorithm that takes in video. So you record some news event, okay? and then the video coder like compresses it and sends it out, and then it's viewed, okay? And afterwards, you ask the video coder, what happened? Did was it a good day or something? And the video coder responds, because it's a video coder, right? So it doesn't talk. It doesn't actually know what's going on. It's just a box, okay, with some computers in it. So the point is this. The thing that's processing the data doesn't have to actually understand what's happening, right? It's just a black box. The two things match, but what's happening in the what the appearance is, there's no interpretation, right? There's absent an interpretation. So that may be very dissatisfying. In fact, it should be very dissatisfying. But it's the first step towards being able to do color. The color appearance is a much more complicated problem. So we're just basically not going to go there. But in practice, in real photography, it used to be, for instance, with chemical photography. So in real photography, you do have to adjust the colors if the surround's different, if the lighting's different, or the colors won't be right. And if you just like faithfully reproduce colors that actually physically existed in the world, they would be very dissatisfying when you looked at them. Mm-hmm. For the same reasons that when you looked at that optical illusion I presented you, the colors look totally different. But it's just, and it's fundamentally an unsolved problem. Okay, so it's a good research topic to go into. Okay, but we're not going to solve it in this class. And if you want to understand color perception, what's called color appearance, and it's also related to what's called color constancy. Okay, so you can consider taking. There's a follow-on course whose number I forget, but it's taught by Professor Albach, and it's on color imaging and other kinds of topics that are related to that. Does anybody know what the number of the course is?
638.
638? Yeah, okay. 638. So it's ECE. So he goes into that in a lot more depth. This is just an introduction to color imagery. So your question is an excellent one, and I have no answer. All right? But let's at least try to understand this first. So does this make sense? Okay. Okay, good. Now, the next the problem is that now the color matching functions, like, let's switch back to the computer. And the color matching function here goes negative, and then it goes positive. So it's if you wanted to have a camera which captured this tristimulus component of red, it would be a problem because you'd have to have a negative sensitivity to light in this wavelength. Now you could do it. What you'd have to do is you'd have to have basically two sensors, one for the positive part and one for the negative, and then you'd have to subtract the negative part from the positive part, right? But it would be a pain, okay? It would be complicated, okay? So the question is, can you produce a color matching functions which are positive, so you don't have to deal with the negative components? Interestingly, there's some interpretation here, which it says that something seems redder if you actually. Hold on for a second. There's some interesting. Well, I'm going to. Yeah, never mind. I won't even try to get into the interpretation. There actually is an interpretation, but it's too complicated to explain yet. Okay, so these are the three curves. So what are you supposed to do? Well, you can do a linear transformation. So you can say, can I find three strictly positive curves which subtend the same basis? And the answer is, well, you certainly should be able to, because remember that physically the retina of your eye contains cones, and unless the cones have negative, it's conceivable that the cones could have negative sensitivity, but they don't. And in the beginning, we actually had, is that on this slide? Maybe that's not on this slide. On a previous slide, let me see if I can, was it here? Oh, yeah. So these are the LMS. Those are strictly positive. And those are the responses now of the actual cones in your eye. So these should be a linear combination of the other functions. Put another way, those functions that we have measured have to be a linear combination of these. Now, of course, where did these come from? It begs the question. Let's not worry about that, right? But, I mean, basically, it must be that these are linear combinations of each other. In fact, they're not exactly linear combinations, and the reason is more social than scientific because, well, these are two different communities of people who have measured it separately, so they're not exactly equal, okay? But to the extent they're not equal, well, I mean, there can be some higher order effects and so forth, but mostly they're just two different standards. So they're not precisely equal numerically. In fact, in their lab, I think there's some part where you have to transfer between LMS and XYZ or RGB, and the transfer is not exact, okay? Because they're not, in an ideal world, they would be linearly related, but they're not. But in any case, this is motivation that shows that there should be some coordinate system in which the color matching functions are strictly positive, okay? Okay, so, hold on. So you can fiddle around with this, and some magic occurs, which will later actually be justified. But for now, it's just going to be magic. Okay, so you have these three color matching functions. If the three color matching functions, if you apply some, imagine, hold on. Oh, I went a little too far. That's the problem. Okay. Okay, here we are. Okay. So a color, say, is formed by a linear combination of R, G, and B. So that means if I take the product of each of, this is really a 31 by 3-dimensional matrix. So this is a tall, thin matrix, right? And if I multiply it by this 3-dimensional vector, I take a linear combination of these column vectors to produce a color, right? And the values of RGB must be the integral of the associated matching function with the spectrum of the incoming light, okay? Now, I already talked about this. That we're going to assume that the color matching functions are scaled so that they integrate to 1 without loss of generality. And in that case, equal energy white, which has uniform spectral density from over all wavelengths, is going to correspond to RGB values of 111, or 111 times some constant. Okay. Now, I told you that we want to try to find new color coordinates which are strictly positive. So the new color matching functions, which we're going to call X, Y, and Z, so they're going to be tristimulus values that we're going to call X, Y, Z. And in color, when working in color, the symbols uppercase and lowercase X, Y, and Z are reserved. Okay, so it's sort of like if the computer scientists would say it's a polluted namespace. But if you yeah, thank you. That's exactly what I wanted you to do. It's amazing. You read my mind. Okay, so X, Y, and Z. Okay, and X, Y, and Z, right? And then the other ones that you can't really use, maybe you could get away with a little more, but basically I would avoid them, are L, A, and B. So you basically just can't use these symbols for anything else. This would be like if you were writing a formula and you were saying 3 pi plus 2 equals 6, okay? People would be totally confused as to what you meant. I mean, you can't use pi as a variable, okay? Because everybody knows pi is the ratio of the circumference to the diameter of a circle, right? If you start using it as a variable, they'll be totally confused, okay? Okay. So in color, if you start using X, Y, and Z for other things, no one's going to know what you're talking about, okay? Because X, Y, and Z have a hardwired meaning, okay? Don't hold me responsible. I didn't make the rules, okay? Okay. Now, go back to the computer. So, over here, then little x, little y, and little z0 are the color matching functions. Now, that's my notation of using little x with a lambda. That's not so standard. But the uppercase and the lowercase x's are absolutely standard notation. Okay. Now you want these three functions now to be strictly positive. So the question is, how are you going to do that? Well, you have to find a linear combination, and it turns out there is such a linear combination. So at this point, it's going to be magic. We just take this 3x3 matrix, we multiply it by the color matching functions. Okay, I guess in this case, yeah, the color matching functions are row vectors. So this is going to be a 3 by 31 dimensional matrix, which you multiply by m, and you get then a 3 by 31 dimensional matrix. And the rows of this matrix are going to be the color matching functions for x, y, z. Okay, and m here has the following entries. So this is just standard. Okay, it comes from the definition of x, y, z, and I think this is for the 2-degree observer. Okay, so if you plug these in, miraculously it will come out that the color matching functions are greater than or equal to 0 for every lambda between 400 and 700 nanometers. And this thing's constructed that way. Furthermore, if these color matching functions have unit area under them, then they'll have unit area. Then the new color matching functions will also have a unit area. And the way you can show that is that, let's see. So I guess the rows of m have to sum to 1. Now, hopefully I'm right about this. Either the rows or the columns. Okay, yeah, because the 1 here in the 9 carries 1. So this is 5. This is 0.5 plus 0.3 plus 0.2. So see, it sums to 1. I didn't make it up. Well, maybe I did make it up, but then I got very lucky. Okay, so the rows have to sum to 1. Okay? Okay, good. If they don't sum to 1, we'd have a problem. So now, when you apply that, you get color matching functions, which are strictly positive. So that's good. Okay, now here, what you can see is to produce, now X, has the interpretation of being a supersaturated red. Y is like a supersaturated green, and Z is a supersaturated blue. Okay? Okay, now why would that be? Okay, now these are not spectra, as I pointed out. They're functions. And it turns out so interestingly enough, to make the reddest red here, you don't just want something over here at the long wavelengths, you also want something at the short wavelengths, oddly enough. Okay, well, because this has like 2 lobes in it, right? Okay, now, okay, fine. Now, so everything seems all hunky-dory, okay? Because what will happen is now you'll get out of here the values of x, y, z. So the tristimulus values produced by this are x, y, z. So x, y, z will be the associated tristimulus values. So by definition, they're the inner product of these color matching functions with I. And I can calculate those by taking m times the color matching functions for RGB. And then I can take m out of the integral, so I get this. So I get that the tristimulus values in x, y, z are the RGB tristimulus values times m. And as I said, x, y, and z have to be reserved. And you use uppercase letter for the tristimulus values. So now the question is, okay, fine. So now, let's say I built a camera and I got x, y, z out of it. Now I want to display the image that corresponding to this x, y, z output. Now how do I display it? Well, I have to use the appropriate primaries, right? Okay, so let's calculate what the primaries are. So what are the primaries? Oh, well, okay. Okay, so we have this thing here. And now, hold on, the primaries, okay, so the color is going to be x, y, z times the associated primaries, which I'll call capital X, uppercase X, uppercase Y, and uppercase Z, right? So that's going to be the same thing as RGB times RGB primaries, right? But RGB is XYZ. RGB times M is XYZ, so XYZ times M inverse is RGB, so I get this. But then if I plug in I calculate M inverse, I get these numbers here. But these are negative. So how am I going to work this? Because I have to have negative amounts of primary in order to calculate the primaries for XYZ. Well, it could have been that I just picked bad choices for primaries. These particular primaries are associated with this is the CIE RGB primaries. It could have been with some other primaries, maybe that matrix wouldn't have negative entries in it. But it's going to turn out that that's not the case. There are no primaries which you can combine together RGB to produce these primaries. Okay, said another way, it's going to turn out that you can prove that there are no physically real primaries associated with the XYZ coordinate system. So this is just at the moment when you finally thought that you had solved the problem, all your hopes are dashed, okay? Because, well, you fixed the problem of making the color matching functions positive, but unfortunately, in your zeal to fix that problem, you created non-existent primary colors. So, what are you supposed to do? Okay, well, the answer is that largely there is no real answer. That so the primaries for XYZ are non-real primary. They're not physical. So they're said to be imaginary colors. A little bit like the idea of imaginary numbers, like the square root of -1. Only I think these are more imaginary than imaginary numbers. My feeling is imaginary numbers are no less or more real than real numbers. But imaginary colors really are imaginary because you just don't exist, okay? There's no such color in the sense that you cannot produce a stimulus that a human being will respond to in the way that primary is supposed to create the desired response. It just doesn't physically exist. You can talk about it existing mathematically, but it doesn't exist physically. There is no such color. So you're saying, well, what does that mean, okay? Well, we're going to hold on. You're going to find out. But the bottom line is this. RGB colors represent real primaries. So the advantage of those tri-stimulus values is that the primaries can actually be produced. If you want to physically make a device with 3 primaries, like a display, you've got to pick physically real primaries because it's the only thing you can produce. But if you make a capture device, the capture device for those primaries is going to be a problem because it has to have negative response in certain spectral ranges. So there's a trade-off. You can capture in XYZ, but you have to convert to RGB when you want to display. So, okay, now, in order to have a better understanding of why all this happens, alternative. Okay. This is I can tell you why. Okay, we're going to find out later why all this happens with the XYZ color primaries. But I'm going to back up at this point and cover another topic, which is hopefully gives you a little bit more insight into how color works. Okay, and what I'm going to talk about is sort of an interpretation of RGB. It's very simplistic in the sense of additive and subtractive colors. One thing that comes up a lot in color imaging is that you can there's 2 sort of basic ways of describing color that occurs in physical systems, and one is the additive color system, and the other one is subtractive. Okay, now if you turn on the red, green, and blue components of an image on a display, what color do you get? You get white. Okay. Now, I don't know. How many people in this room were children? I'm waiting for somebody not to put up their hand.
Some of us still are.
Okay. Because they're from Mars. Okay. All right. So I assume everybody here was a child at one time, right? Okay. Now, when you were young, okay, did you ever have watercolor paints? Okay. Now, when you had the watercolor paints, did you ever try mixing all the colors together?
It's flat.
Now, anybody who didn't try mixing all the colors together, I'm really concerned about. Okay, now, what color did you get when you mixed all the colors together?
It's flat.
Black.
You get kind of black, okay? Well, dark, muddy kind of color, right? So, what went wrong? How come when you mix all the colors together, you got black, but when you put all the colors on the display, you get white?
It's additive. They use different primaries, I think.
When
Yellow
you took
one, right?
red,
that's the
red,
same.
green, and blue paint, and you mix them together, would you get white, you think? It'll get black, or at least dark.
Yeah.
So, what's going on?
Additive.
Huh?
It's additive.
Yeah, one's additive and the other one's subtractive. Okay, so I'm going to just cover this at the most excruciatingly basic level. Okay? But, I mean, just so you have some orientation in this issue. Okay, so first of all, okay, so this matrix M. I guess I forgot to point this out. That the matrix M, the columns of this matrix represent. Hold on for a second. Let's skip this. Never mind. Okay, let's just go right here. Okay, this is black. K is often used for black. If you add red and blue and green in an emissive display, the light is adding together. So in that case, what happens is that you have these three basis vectors associated with red, green, and blue, okay? And the color is a linear combination. That's what we've talked about so far, okay? So in this coordinate system, red is 1, 0, 0, green is 0, 1, 0, and blue is 0, 0, 1, okay? Now, so what happened, I got to tell you this because this is a little surprising. Okay, so if you take blue and green and you add it together, what do you think you get?
Yes,
You get a bluish green, right? And that's reasonable, because if you said, what color is your car? And I said, oh, it's a bluish green, you would know what I was talking about, right? Okay. If you add blue and red together, okay, what color do you get?
A bluish red.
You get a bluish red, okay, which is purple, okay? So if I said my car is bluish red, you'd say, well, that's a little strange. Why didn't you just tell me it was purple? But okay, all right. It'd also be kind of an ugly car, but that's another matter. Okay. Now, if I add red and green together, what color do I get? You get yellow. But does yellow seem like a reddish green? If I told you my car was yellowish green, no, reddish green. It's reddish green, okay? What color would you imagine as being reddish green?
Brown.
Yeah, I don't think it's good. Yeah, that'd be about as good a color as I could have come up with, okay? But certainly yellow wouldn't seem to be in the cards, okay? Okay, so that actually is an interesting observation because it's a result of the fact that the color perception is believed to be the current theory of color, which, like most physical theories, is updated periodically. But the current theory of color is the so-called opponent theory, okay? And red and green are opponent colors. So, you can think of green as, say, positive and red as negative. So when you say reddish green, you're saying a positive negative-ish number, okay? They're mutually contradictory. So consequently, when you add them on the monitor, what you get is yellow. But the first time I actually performed that experiment, I was surprised. I thought maybe I had a bug in my program, okay? It didn't seem right. But then you say, well, yeah, it is a bright color. If you think about it as yellow as being white minus blue, then it makes more sense. If you remove the blue from white, it seems kind of more sensible. The other axis in the opponent color system is blue-yellow. Okay? So anyway, greenish blue is cyan, okay, which is greenish blue, and reddish blue is magenta, which is purplish, okay? Okay. Now, if you add all three together, you get white. So, okay, so the cyan is 0, 1, 1, magenta is 1, 0, 1, and yellow is 1, 1, 0. And if you add them all together, you get white, and that's 1, 1, 1, okay? Now, if you go to a subtractive system, then what you can do is you can say, well, okay, I can represent the color as, instead of representing it as the combination of red, green, and blue, I can represent it as white minus something. So I can just manipulate the equations, and I get, if I define 1 minus red, 1 minus green, and 1 minus blue to be cyan, magenta, and yellow, the tristimulus components, then I can think of cyan, magenta, and yellow as basis vectors in which I subtract red, green, corresponding components of red, green, and blue from white. And that's what happens in a subtractive color system. So in a subtractive color system, you start at white, and then if you subtract blue, you get the yellow. If you subtract red, so you have RGB, okay, and then cyan, CMY, cyan, magenta, yellow. So cyan is very roughly speaking, 1 minus red, or at least you can formally just define it that way. It's 1 minus red, magenta is 1 minus green, and yellow is 1 minus blue. Okay, and then in that coordinate system, then the cyan is produced by, if we switch back to the computer, the cyan is produced by subtracting it's subtracting red from the white. And the magenta is produced by subtracting green from the white. And then yellow is produced by subtracting blue from the white. And then if we subtract all the colors from white, we get black. Yeah.
I confused because when we add all of them together, we should get a very white.
That's correct.
But when we want to subtract them, we just have white.
So if you start with, the reason subtractive color systems come into play is because in printing or in painting, you start with white paper, say, and then you put dyes on it or pigments that absorb light. So in a subtractive color system, you can only remove light. You can't add it. So in other words, let's say, assuming the paints or pigments or dyes you use are not fluorescent, then when the light hits them, the spectrum of light that hits it at any wavelength, it can only reduce the amount of reflected light from the light source. So if you have white paper and the white paper is not fluorescent, typically white paper is fluorescent, but let's say it's just a neutral white paper that just reflects all the light that hits it, then the color of the paper will actually, if you measured it, well, not the color, the spectrum of light coming from the paper will actually be the color of the illuminant.
The color of illuminant should be at least 3 times whiter than paper.
Well, the illuminant can be any color, but you will normally perceive the illuminant as white because you do sort of a correction for the illuminant. Your brain, that's one of the important reasons that your perceived color differs from it can't be calculated just as a function of the spectrum of light, because your brain makes a correction so that it sees a property which is invariant to the illuminant, at least to some degree, and primarily dependent upon the properties of the material. That's why you associate color with objects, okay?
Our brain normalizes.
Your brain normalizes what it sees, okay, in a very sophisticated way that goes beyond the scope of this course. Okay. So, so is that clear? At least, yeah. And hopefully, what I'm doing is stimulating your interest in taking the follow-on course. Actually, you know. Okay. So, Okay, now to get this gives just a cursory sense of what's going on. The light, if you have a paper, the light enters the paper, bounces around, and comes out in a random direction. Okay, and there's various cosines and sines and so forth. But what happens is that the energy of the spectrum per unit surface area falls off as, I think, 1 over the cosine. No, it falls off as the cosine. And then what happens is, but you see, as you tilt the paper, so let's say you're looking at an angle, you're seeing in a unit amount of angular, if you're looking over 1 milliradian or something, right? One fixed unit of angular, of angle, then the amount of paper you see increases as you tilt it more, okay? So those two things cancel out, and the upshot is that for a perfect Lambertian surface, which is what happens if light goes into a very, let's say, a powdery surface that consists of, it goes in and bounces around and is completely randomized in its direction. So for a perfect Lambertian surface, if you look at it, then the visual intensity of the surface is invariant to the angle. So a good example of that is, and you can come back to the piece of paper now. A good example of that is, so, do you know what that is?
Trees.
Oh yeah, I'm a really good artist. Okay, good. Okay, on a night on a clear night, right? You see the moon, right? And the moon in that case is technically known to be in the sky like a big pizza pie, right? So it's flat. It looks like a pizza pie because pizza pies look flat, okay? So why is that? Because the surface of the moon is a Lambertian surface approximately. It's got a lot of very fine dust on it. And the light intensity is invariant to position, even though this is a sphere, right? Or approximately a sphere. So the angle is high here and high here, but it's flat there. The light reflected from the surface appears to be, the illumination looks uniform, approximately, right? So that's because it's a Lambertian surface. So that's a good way to remember that, okay? That's what a Lambertian surface is, okay? So coming back to the computer, this is a Lambertian surface, and in that case, now what will happen is that, and this, by the way, also explains why foam is always white. Like beer foam's white, the foam at the sea. I mean, if you go swimming and the foam is not white, like leave immediately, okay? Okay. So, snow is white. All those things are white because the light goes in, bounces around. It's not absorbed. It just is reflected out at random angles, like a Lambertian surface, and it appears white. Okay. Now, so what happens now is it won't appear white if there's dyes or impurities that would absorb the light. That would be a function of spectrum. Okay, wavelength. Okay. So if you put ink on the surface of the paper, what happens is the light's going in, it gets absorbed. Now, the absorption is a nonlinear effect, just like we talked about with tomography, because it absorbs exponentially. That's so-called Beer's law. So as it's going in, it's absorbed exponentially, and then it's reflecting, but it's a multiplicative effect. So what happens is that, and this is very approximate, okay? First of all, there's a variety of things that can happen. You can have, this is a so-called dot, okay? That's a very technical term, dot, okay? So you have a dot of ink, okay? And you can have the dot on the dot, or you can have the dot off the dot, okay? If the dot's off the dot, then there's no interaction between the dots. If the dot's on the dot, there's going to be interaction. They're going to multiply together. And if they're partially on, well, then it gets more complicated, right? So, but at least in some very simplistic case, you could say, well, whatever the absorption is due to the magenta. Oh, I'm out of time. I was just getting fun. Okay, well, we'll finish it up on Monday. See you then. Enjoy your weekend. Bye.